Thank you for the introduction. Ladies and gentlemen, I would like to tell you more about how to get started with deep learning in radiology and medical imaging. These are my disclosures. So how do you get started? Well, the easiest way is just to become friends with a computer scientist. Another way to get started is to do everything yourself. But during this talk, I'm going to talk about the more professional way and building a team and doing everything according to the book. So before a deep learning algorithm can be used in a clinical setting, many steps need to be taken. And Montagnon and colleagues present in their paper that was published in Insights into Imaging this year a checklist of things that you need to go by before you can develop your algorithm. And I extracted the 4 most important points. So let's focus on the steps that will help you to get started. First is define the scope of the project. The second step is make sure to work with the right people so that you have clinical, imaging, and technical expertise on your team. And the third step is to make sure that you either prepare your data or that you use publicly available data. And the last step is to train, validate, and test your model. Let's start with the first step, the scope. It's obviously essential that you're solving a clinically relevant problem. And there are different ways that you can apply machine learning or deep learning for. One of the problems that it can solve is, for example, a segmentation problem. Here we have a CT scan of the abdomen, and for example, we want to develop an algorithm that evaluates kidney cysts. And one thing is that you can do segmentations. So every voxel is determined to be part of the lesion or not. Another thing that you can do is detection. So you can see whether the renal cyst is present or not. Or classification, so you can have multiple classes. For example, this lesion is benign, malignant, or it's indeterminate. And another essential part of machine learning is risk prediction. For example, this lesion has a 0.8% risk for cancer. So an example from our group is a segmentation problem that Louis Hahn worked on. So what he did is he developed an algorithm that automatically segments the true lumen and the false lumen in patients with initially uncomplicated type B aortic dissections on CT angiography exams. He first identified or localized the aorta, and then he drew a center line which was used for multiplanar reconstructions, and the algorithm was actually developed on these images determining the true lumen and the false lumen. And then optionally there was a back conversion step to the actual plane so that you can see the true lumen and the false lumen in the actual plane. Another problem that we solved within our own group was a prediction problem. And when you look at Netflix or Amazon or Spotify, they often use market basket analysis. So one example is if somebody goes to a grocery store and buys flour and sugar, there is a high probability that this person also buys eggs. And this analysis, market basket analysis, is used a lot in the non-clinical world. And we try to evaluate if this maybe worked in the clinical setting. So we developed an association rule learning algorithm in patients that got CT scans with iodine contrast. And we wanted to see if we could predict if patients got acute kidney injury. So with the association rule learning method, you get different rules, which means that all these dots here are different rules, and each rule has different parameters. For example, this is a rule with a 100% confidence that this patient will develop acute kidney injury, and only if patients have a weight between 80 and 90 kilogram, if the iodine is 300 milligrams per milliliter, the concentration, and if this patient had a CKD stage 5 or end-stage kidney disease. If those combinations were present, then this algorithm said there's a 100% confidence that this patient will develop acute kidney injury after the CT scan. So this is one of the applications that machine learning can help with, and it's prediction. So once we've determined the clinical scope and we determined what method we're going to use, then we can look at what team is going to solve this. So ideally, the team would consist not only of you, the imaging expert, ideally there would also be a clinician to make sure that the developed model will be clinically relevant. And of course, you'll also need a technical expert to develop the actual algorithm. So once we've built a team, we can continue and work on our data. There are 2 ways how we can get data. We can either use publicly available data, or we can prepare or curate our own data. So depending on the question that you have, you can download data that's already publicly available. Some examples are the Cancer Imaging Archive, RSNA Kaggle challenges, and Stanford also has some data sets available. So if this is in line with your question, then you can just use this. And there are actually way more large open source medical imaging data libraries. And this is a list of some of them. So this works very well if you want to develop an academic research project. If you want to develop a commercially available algorithm, you'll need more than just the publicly available data. But this is definitely enough for you to get started. But if you have a specific question that you cannot solve with the data that's publicly available, you'll need to prepare or curate your own data. And to do that, there are different steps that you need to go through. First, you'll need ethical approval. After ethical approval, you'll actually get access to your unprocessed image data. After getting access, you need to query the data. So you need to make sure that you search for the right data that you need to solve your problem. After querying, you need to de-identify the data, and then you can transfer it either to a local, for example, if you have a single center study, or to an external storage, for example, if you have a multi-center study, and this can, for example, be in the cloud. After that, you need to control for the quality, you need to structure your data, and potentially you can label your data. So all these steps you need to go through to prepare and curate your data. If you want to learn more about this, this year, my co-founders of my startup and some of our advisors and friends and me published this paper in Radiology about preparing medical imaging data for machine learning. Also, on Sunday, Les Folio and I will give a workshop on how to prepare medical imaging data for machine learning. Okay, so once we have the whole curated data set, we are going to have to divide it into a training, validation, and test data sets. It's recommended to perform the splitting at the very beginning of the workflow, to keep the test data unseen to the model till the final performance evaluation. So it's very important to keep this separate from this part. And mostly when you are dealing with a very large data set, this is the division that's being used. So based on the training data, an initial model is trained, result in a trained model. The next step is to validate the model, so to monitor the performance and potentially to calibrate it so that you get a fine-tuned model. And then the last step is to see how the fine-tuned model performs in the test data set. So you can evaluate the final model. Then if you see that it's still not performing well, you can actually go back to the training and optimize the model. And this can iterate multiple times until you finally have your deployment ready model. So there are different data sampling strategies. It's common to divide it into training data, so to include the validation data into the training data and to have the test data separate, because that's very important. If you have a smaller data set, oftentimes cross-validation is used, and the mostly used method is actually k-fold cross-validation. So you cross-validate the training data. And how does this work? Well, you split your data into multiple little pieces, and one piece is validation set and the rest is training sets. And once you have done the cross-validation, you can go to the test data and see if your model still performs well. So let's dive a little bit more into the cross-validation. So the data is divided into k subsets of validation sets and training sets. And there are k rounds, so number k rounds, and every round another part of the data is determined as the validation set. So here it's this one, here it's this one, here it's this one, and so on. And for every round, you can determine what the accuracy is. So we see different accuracies for every round. Then if we want to determine what the accuracy for the whole data set is, then we can just take the average of all the rounds, and in this case that would be around 92%. So after we have done this, after we've done the cross-validation, now we can go to the test set and see how the model performs. So this is called k-fold cross-validation. So once we have the data complete, we can now focus on the actual model development. And everybody has seen this graph multiple times, obviously. Deep learning is part of machine learning, which is part of artificial intelligence. There are different model types that you can use. For example, classification, regression, and clustering. And I will show some examples here. classification, we have malignant lesions and benign lesions with a specific diameter and density. What if we have another lesion, an unknown whether it's malignant or benign, and we want to determine what it is? There are different ways we can use, we can evaluate this. For example, the nearest neighbor classification just looks at what dot is closest to this one, and that's probably is what it is going to be. This is not a very advanced method, but it gives you an indication. So according to the nearest neighbor classification, this one would be benign. Then another method is, for example, the k-nearest neighbor classification. And if you define k as 5, then it will look at the 5 nearest dots. And you see that 3 of them are malignant and 2 are benign. So in this way, we would say this one is probably malignant. Regression. We have here age and calcium score on the horizontal and the vertical axis. We can, for example, do a least square regression, which is a very basic form of machine learning, in which you just do a linear regression and then you know the age of the patient, and then you can predict the calcium score just based on this simple linear regression. Clustering, an oftentimes used method is k-means clustering, so you just have clusters of data and you determine which points belong to which cluster. Then there is unsupervised and supervised learning. So in unsupervised learning, we don't know exactly what the clusters are. In supervised learning, we know that this, for example, these are the malignant patients and these are the benign patients. If you want to learn more about how to actually apply all this, I recommend some Coursera courses about machine learning and CNN and Python courses to actually apply all of this. So in short, it's important to determine your scope, to build a good team, to prepare your data well, and then to build your model. Thank you for your attention.